Okay, now we move on to problem 4. Problem 4 says that if you draw 5 cards out of the standard deck of 52 cards, what is the expected number of queens you get? So if we first look at this question, we know that this question is a hypergeometric distribution. So one way to solve this problem is to look up at the table, if you have one, the expectation of hypergeometric distribution and plug it in the formula. But in a lot of cases, it is like a little bit hard, and if you don't like remember the formula, it's very hard to derive in one like certain like a small short time period. So I'm actually introduce another way of solving this problem. So that's like approach 1, and approach 2 is to split up the random variable. So let's say like y is defined to be the number of queens in your hand, and let y1 to be the random variable that is like a indicator. It can but it is also a random variable that is 0 if the first card is not a queen, and is 1 if the first card is a queen. So it can only be 0 or 1. This is like a random variable. And similarly, we define y2 to be if the second card is not a queen, or the second card is a queen. And now y can be just directly, the random variable y is just y1 plus y2 plus y3 plus y4 plus y5. Why is that true? Maybe we can like say an example. Say like for the 5 cards, the second card is a queen. The first one is not. The third one is not. The 4 is a queen, and 5 is not a queen. So you got 2 queens in your second draw and the first draw, or like the second card and fourth card, and that means y equal to 2, and that means like in your hands there are 2 queens, which makes perfect sense. So that's actually called method of using the indicator. Instead of looking from like global perspective, we are looking from like certain individuals' perspective. So in this case, we look through the perspective of each card in my hand. And the good thing about that for like splitting random variable is because y1, y2, y3, y4, y5 are the same. Like they're just like different position of the cards in your hand, but their expectation are all, their like distribution are all the same. As you can see, they are like all 0 or 1, 0 or 1. So they are identically distributed. So if we want to find the expected value of y, that's just the expected value of y1 plus y2 up to y5. And because expectation follows the linear transformation, that's just e of y1 plus e of y2 plus e of y5. And as what I just mentioned, each of the random variable, each of the indicator y1, y2, y3, y4, y5 are all identically distributed. So they are the same. They are just like 5 times e to the y1, or any of them. And another way to think about this the expectation of and also like the expectation of y1 is just 1/13, because there's like 4 queens out of like 52 cards. Yeah, and also like the reason why expected value of this y1 is 13 is because, remember, like, what is the expected value of a random variable? It's like a summation of all possibilities times the probability of that possibility. But like for this indicator y1, it can only be 0 or 1. It's 0 when the probability of the card is not queen, and it is 1 when the probability of the card is a queen. So the expected value is actually just the probability of the card is a queen, and that's why we can like just directly calculate the probability as the expected value. So the answer for expected value of y is just 5 times 1/13, which is roughly equal to 0.38. Okay, and then for problem 5, the question is, you observe a radioactive sample releases an emission on average once every 10 seconds. So that's something important, once every 10 seconds. And what's the probability of there's at least one emission over the course of 1 minute? And what is the expected number of emission in a minute? So we know that from the context, this is a Poisson random variable. And we are now considering some sequence of discrete trials that can succeed or fail. Rather, we are waiting for like time period or and record the number of success, and that's like exactly what the random variable are describing. And the parameter of the random variable is lambda, which is the sum. And in this case, it's equal to 6, because we are looking for its emissions throughout a minute. So a minute has 6 10 seconds. So it has once every 10 seconds. So in a minute, the mean is like 6. So we also know that the expected value of this Poisson distribution is 6, according to like the thing we derived in lecture. And actually the variance is also equal to 6.